Go.
Okay, good morning, everyone. So we are the group Pizza by the Pizza Hut, as we are Anita, Kevin, Zachin, Wendy, and Stephen. So before we start our presentation, I would like to ask everyone a question. If you know the answer, please raise your hand. Does anyone know anything interesting of the Tower of Pisa?
Oh, I know.
Go ahead.
It's in a town called Pisa.
Thank you. Anyone else?
It's in Italy.
Very true. Anyone else? Actually, we'll just move on. Thank you for the responses. The Tower of Pisa is actually very unique in art, and it also has a very charismatic history. And as you guys said, it is also one of the attractions of tourism in Italy. It was used as a freestanding bell tower and an observation in World War II. But it has gone through lots of controversies and lots of pauses in construction. We are interested not only in the artistic value and its historical significance, but more the physics behind it and something fun, as Stephen will explain more of our motivation.
All right, let me take over and do the starter. So let me share something fun about Pisa Tower. Here is the Superman. I believe you all know Superman. It's a movie about between Superman and Pisa Tower in 1983. And it's very cool and interesting. And it's a comics. So we like Superman. And you all have read a passage or learned physics about Galileo's tower experiment, two balls falling down on the ground at the same time. And I think it's the source for us to first knowing about Pisa Tower. And also tourism in Italy. Pisa is the place you have to go if you travel to Italy, and so you can take some really interesting photos, and it's cool. So for the objective of our research or experiments, we are going to simulate the real construction of Pisa Tower to find out that how it's built and also analyze the effects of the tower by the ground condition with the element birth and death with the Epcot ANSYS. All right, let my teammates Wendy take over again.
Hello. Let me introduce about the background of the tower. The tower was first started building in 1173, which is 848 years from now. And the construction of the tower, including 3 stages, and as shown in the picture, is over 200 years. The tower began to sink after the construction has processed to the second floor in 1178, because there's only 3-meter foundations sit in the weak and unstable ground. Then the construction was stopped for almost 1 century. And in 1273, the construction restarts again. In an effort to correct the tilt, the engineers built the upper floors with a side taller than the other sides. Because of this, the tower is actually a curve. Finally, the 7th and the 8th floor was added in 1370. And in the following years, many engineers tried to correct the tower. However, some of them even make the situation become worse. The degree of the tower reached 5.5 degrees in 1990. And let me introduce some real data of the tower. The height of the tower is 55.86 meters, on the lower side and 56.67 meters on the tower side. And the width of the wall at the bottom is 2.44 meters. The height of the 8th floor, you can see in the top here, 8th floor is 3 meters height, and the wall there is 2.48 meters thick. The whole tower is 14,500 metric tons. And the tower has 296 or 94 steps. It is because that in the 7th floor, there's 2 fewer steps on the north side of the tower. Okay, then Anita will give you guys an introduction about the ground condition.
You're muted.
Didn't open your microphone.
Okay, can you guys hear me now? Okay, good. So the subsoil of the tower is constructed based on the alluvial deposits of the Arno River, which is shown in the PowerPoint. And during the last glacial period, world sea levels was dropped by around 100 meters. So the bedrock is filled with alluvial materials, such as silt, sand, clay, and gravel, which is shown on the upper left corner. And the first 60 meters of the depths of the soil has been defined as horizon A, B, and C, as you can see in the PowerPoint. Horizon A is of upper deposits from around 3 to 10 meters. Horizon B is of silty clay deposits from around 10 to 40 meters, while Horizon C is of lower sand deposits from 40 to 60 meters. So above Horizon A, which is around 0 to 3 meters, there was archaeological remains, and the layer is being defined as uneven, so we're not taking that into concern. Horizon A consists of silt, clay, and has a chaotic nature. Does anyone know the word chaotic?
Yeah. It's a mess.
Yeah, so it's like messy because the sediments would deposit in an estuarine environment. So in Chinese, it means 江口的港湾的. So an estuarine environment has fluctuating salinity or saltiness in a water body. So the salt concentration varies with time and tidal conditions. Horizon B, on the other hand, can be subdivided into 4 layers. First of all, there is the upper stratum, which is of uniform gray bluish clay with high plasticity, and that extends to around 21 meters. So this type of clay is defined as the Pancun clay. And the second one is the intermediate and clay and sand layers, which are both similar to the deposits of Horizon A, and they're both very chaotic as well, in that they're deposited in an estuarine environment. And there's the bottom layer of Horizon B, which is a soft clay layer similar to the Pancun clay, and that extends to a layer of 40 meters. And Horizon C, lastly, has an alluvial sands with layers of silt and clay. This layer is similar to the upper clay in that it has a microfauna similar to typical salt water. Therefore, the construction or like the soil structure can be classified as a hamburger. So the bread represents a layer of the estuarine environment, while the lettuce represents the Pancun clay, if that makes sense. Yeah, so as we constructed the tower, as we simulated it, the ground conditions are simplified, and simplification methods will be discussed later. But next of all, let's welcome Qian to talk about his models.
And here's our models. The left one is the tower and the right one is our ground condition. As you can see in the in our tower. The tower is separated in 3 different parts. The first part is the first floor and the second floor, which the foundation. The second part is from the 3rd floor to the 7th floor. And the third part is our 8th floor. And you can also see here is some empty space in our tower. This is to reduce the total volume of our tower to make it more like a real tower. And if we don't do this, remove this place, our tower's weight will be twice about the real tower. And in the right picture is our ground condition. The first floor is plain and there is no any drop in it. The second floor, the second layer has a 3 meters drop, and the rest 3 layer has 1 meter drop respectively. And here is also a small part in there. This is the connection part between the tower and the ground condition. We create this part to change its machine size to get more accurate results. Okay. And Kevin will talk about our methodology in the next part.
So these are our models of 2 different experiments. In these experiments, we just slip the ground into different layer. As you can see, at the left side is a simpler model with only 2 layers, and the one on the right is more complicated. So for the simpler simulation, we used 2 layers of soil with slightly different Poisson's ratio and isotropic elasticity. Then in experiment 2, we changed the ground into sandstone and found that the deformation of the tower is almost identical to the result in which the base of the tower is a fixed support. And the tower, which is made of marble, is like rigid body compared to the soft soil. So it has a little effect on our result. So we could conclude that the tower has less effect on our results. So we could focus on the deformation of the soil. The top layer is relatively softer than the lower layer here. And for the more complicated simulation, we constructed 5 layers with uneven thickness because after reading some pictures, we found that the soil become more and more sandy from the south side to the north. Therefore, we designed the soil like this. You can see here are some detailed data about our model. So at the south side, the second layer, which is made of sand, has 4 meters thickness, and the north side has 3 meters thickness. And here are some specific data about different layers. For example, you can see the layer at the top is harder than the layer at the bottom, the 3rd and 4th layer, because they are made of Bangkok clay and those seals and softer materials compared to sand at the second layer. And we try to construct a suitable mesh for a model. We set whole model into one part to avoid any hanging node. So before I did this, the program was meshing each part individually, so the elements were not connected between different parts. You can see in these pictures, this node and this node right here is not connected to any other nodes, so that may cause some problems. And if we mesh the body as a whole, as one part, all these nodes are connected, so there won't be any hanging nodes. And also, to make sure that we want the solution to not exceed the limitation of the student's version of the of ANSYS, we have to simplify the mesh of the tower, so we can focus more on the ground layers and focused on the analysis of the deformation of the soil and so on. So after simplified, our final mesh has around 7,000 elements. So for the material of the tower, we have we just use the default material in ANSYS, which is marble, and we set the density of the soil to 0 because we want to ignore the effect of gravity on the soil when we add our standard Earth gravity as our load. And for the boundary conditions, we add a fixed support to the bottom of the of our soil, and on the side we added a frictionless support which prevents the soil from expanding to the side, and it only allows a vertical movement of the soil. And all the parts, including the base and the soil, are set to be bonded. This is our main method. We used element burst and depth to simulate the real construction of the tower. So in step 1, we only set the first body, which is the base of the tower, to be alive, and we kill the second and third floors. And then in step 2 and step 3, we gradually brought the second and the third floor alive. That it's like a real construction of the tower, and we watch the effect of adding each floor on the deformation of the soil and the tilting. So Ziqian will then talk about our results.
Okay, I will talk about our results for those 3 experiments. And you can see here are some interesting emotion pictures. And here is the result for the experiment 1. The right left one is this one is our equivalent stress picture, and you can see the maximum stress concentration point is in the first part. In in this point. And this one is our total deformation results. You can see compared to the solid, the whole tower is like a rigid body, so it goes down together with those 3 parts. And this one is our x directional deformation. The maximum point is here in the south side ground, and here in the north side underground. This was caused by the tower's gravity, like that. And compared to the ground, it likes a rigid body, so it seems to give a bending moment to the ground condition to here. And we have a bending moment here. Then the soil has two rotation in this way. And this is our experiment too. The ground condition was from soil change to the sandstone. The maximum stress concentrate point is the same with the experiment 1. However, the total deformations is different with the experiment 1. As you can see, the maximum point is on the top of our tower. Because compared to the ground condition, our tower makes by a mix of the marble. The ground condition is the sandstone. It is more like a rigid body, so the tower could not be go down. It just has a small deformation by its own gravity. And the third picture is our x-directional deformation. As you can see, our ground condition is a rigid body, so the hold parts, the tower and the ground condition move together to this way. And here is our third experiment. The same as those two before, experiment 1 and experiment 2, the maximum stress concentration point is the same. And the total deformation and x-directional deformation is very similar to the first experiments. Its only has some date difference. And when we use these 5-layer models, you can see the maximum x-directional deformation is only 14 millimeters. After our calculation, the slide degree is about 5.9. This is set by designed by us, and when we add this maximum x-directional deformation to this, it only rises to 4.92. So this could prove that the constraint of the tower didn't influence the silt of the whole tower very much. The main reason was caused by our ground condition, like that. Okay, in next part, Kevin will introduce our conclusion.
So for conclusion, if we look at the results the changes showed us, we can find that the location of the maximum point, a maximum equivalent stress, and our value of the stress does not change. So we could conclude that the point of maximum stress of the tower should be located near the ground at the south side of the tower. And also through comparing the deformation data from other experiments, we could see more significant deformation with softer material, which is consistent with the reality. And after experiment 3 was modeled and performed, the degree of the tilt rose. So which means we can get a more accurate result. And then my teammates will talk about our recommendations.
let me take an for recommendation for future work. First, for more precise and working results, since we are now using student version of ANSYS and there are lack of some important features, I believe. So a more advanced ANSYS is required for us to get a better result and find out more about the tower. Second, we should not only considering restoring the tower as a math problem, we should consider problem in all aspects. It's an all-around question, not only the soil condition or the structure itself, but also like weathering or tourism, for example, may also make the make it different. Third, we should continue the current methodology starting from 2008, I believe, to extract the soil of the ground. Since from the experiments or the research, we find out that the structure itself doesn't matter so much as the ground conditions. So extracting soil is the good way for us to keep restoring the tower. All right. So these are our picture references to the pictures we used in our PowerPoint. So it's our team. Thank you. That's our team on the squad. Thank you.
Thank you.
Do you have any questions?
Professor, we can't hear you.
If you keep on restoring the tower and it goes straight, then they will lose business.
True, that's true.
I have one more question, one more comment. The maximum stress you quantified on the south side. What about the stress on the north side? Because people are actually concerned about the stress on the north side becoming zero. Once it becomes zero, it signals the onset of the tower lifting up away from the soil. Do you have any comment on that? Did you track the stress on the north side of the tower?
No.
Yes, but actually we can see from the diagram, although the maximum point is at the south side, but at the north side, you can see the color is relatively blue and dark blue, so it should be about 3.4 or even, yes, just 3/4 times, about smaller than the south side. So it's not zero, because in our model we set the base of the tower to be bounded with the ground, so it will not be lifted up. If we add a friction support, maybe if the force is too big, the tower will tilt too much, and the stress will be much smaller.
Yes, in our experiment, the maximum stress is only 3.7 millions Pascal. So I think it's too small. Maybe it's caused by the element limits by the student's version, because our whole part is only has 7,000 elements.
But the stress is not negative on the north.
Yeah, it's not negative.
Yes, it's not.
Yeah, on the north, actually, if you look at the counterpart of the maximum point, there is also a bit of orange and a bit of yellow if you look closely. I might just share the screen. So around here, as you can see, it's a little bit orange on like the same level of elevation, which will be around 2.3776 million Pascal. I feel like this is also due to the limitation of nodes and I mean the limitation of elements, but I don't think the stress would be negative.
Okay, great. Any other question from everyone? No questions, so I am going to stop the recording.